In this video, we're going to be talking about electron configuration, which is a way that we can represent the arrangement of electrons in an atom in a single line of text. So essentially, it is exactly the same thing as what we were doing in the previous video with showing where all of the electrons are arranged, what orbitals and what subshells and what shells your electrons are in, but instead of filling out a big picture, we're going to have a single line of text that conveys the same information. So this is known as electron configuration. Which describes the location of all electrons in an atom in a single line of text. So it identifies occupied, meaning just has electrons in it, identifies occupied subshells in increasing energy order. And how many electrons are present in each. So for example, if we want to write the electron configuration for hydrogen, hydrogen is element number 1. It has 1 electron, so there's only 1 electron we need to place. We're still following all of the same rules, the Aufbau principle, the Pauli principle, and the Hund's rule. So for hydrogen, we're going to have 1 electron, and it's going to go in the lowest energy orbital available, which is the 1s. So if we wanted to describe in words, in a sentence, how the electron, or where the electron is in hydrogen, we would say hydrogen has 1 electron in the 1s orbital or in the 1s subshell. To describe this as an electron configuration, we use a certain formatting. So the electron configuration for hydrogen would be read as 1s1. So the big number here, the sort of coefficient, tells you what shell you're in. The letter would be S, P, D, or F, tells you which subshell you're in. And this superscript 1 is the number of electrons in that subshell. So 1s1 is the complete electron configuration for hydrogen. If we wanted to do the same thing for helium, helium has 2 electrons, and those can both still go in the 1s subshell because that can hold a maximum of 2 electrons. So our electron configuration for helium would be 1s2. So the only thing that changes is the number of electrons in the subshell. They're still in the same place. If we move on to lithium, it has a total of 3 electrons, but we can't put 3 electrons all in the same orbital. So the first 2 electrons go in the 1s subshell, and then we move on to the next highest thing in energy for our third and final electron, which would go in the 2s subshell. So lithium has 2 electrons in the 1s, 1 electron in the 2s. If we wanted to write the electron configuration for this, we would write that as 1s2 2s1. So each superscript is showing you how many electrons are in the subshell listed before it. So this is describing where all of the electrons are in a lithium atom. Let's jump ahead a little bit and try oxygen. So why don't you pause here and try this one on your own. You might want to refer back to your orbital diagrams from yesterday to get sort of the order of things, but see if you can write the electron configuration for oxygen. So oxygen is going to have a total of 8 electrons. The first 2 can go in the 1s. The next 2 can go in the 2s. And then the remaining 4 will end up in the 2p. So this one's a little bit more complicated, a little bit longer of a configuration. So if we want to write our electron configuration for this, we would have 1s2, 2s2, 2p4, and that would be our electron configuration for oxygen. So you can use the diagrams that we were using in the previous video to help you determine the order of the subshells, but you won't always have one of those available to you. But the good news is you don't have to memorize the order either. So we talked in the previous video about how the order gets a little weird once you start to get D and F orbitals involved, that the shells start kind of overlapping each other in energy. And so it can seem a little bit confusing, like what order do these go in? How am I going to remember this? But the good news is it is built into the periodic table. So the energy order of the subshells can be found in the periodic table. So we are all familiar with the periodic table and the shape of the periodic table, and that the shape of the periodic table is a little bit weird, that if you think about it, like why isn't it just a rectangle? Why is it this kind of wonky, lumpy shape that we have? And the reason is actually embedded in the quantum mechanics, is embedded in the electronic structure of the atom. So if we take a look at the periodic table, I left myself too much space. If we take a look at a periodic table, we can kind of break it down into chunks. So we have this tall part on the left as sort of one piece of our periodic table. We have, oops, no, go back where I put you. We have this low part in the middle. Doesn't want to be nice to me. We have this part over on the right that's a little bit taller. I am leaving helium out of this block for a reason. We'll talk about it in a moment. And then we have these little friends off by themselves, not connected to anything else, down the bottom. So if we look at these 4 sections of the periodic table, and think about how these relate to atomic structure, because they do. If we think about the different types of orbitals that we have, the different shapes of orbitals that we have, and the subshells that they create, the simplest we have is the s orbital. There's one s orbital in an s subshell. That orbital can hold 2 electrons. You will notice that, it's probably good, this portion of the periodic table is 2 columns wide. The next shape that we have is the P, orbitals. P orbitals always come in threes in a subshell. So if there are 3 orbitals in a subshell, each orbital can hold 2 electrons. That is a total of 6 electrons that can be held in a P subshell. You will notice that this section over on the right of the periodic table is 6 columns wide. Next up, we have the D subshells, the D orbitals, which come in 5s. There are 5 orbitals in a subshell and each orbital can hold 2. That means our subshell can hold 10 electrons total. And you will notice that this section of the periodic table is 10 columns wide, seeing a trend here. And last but not least, we have the F orbitals. There are 7 of those within an F subshell. So that means the F subshell and F subshell can hold 14 electrons, and you will notice that this section of the periodic table is 14 columns wide. This is not a coincidence. It is because the electronic structure is kind of built into the way that elements are organized. So we often refer to these as blocks of the periodic table, that this first block on the left is known as the S block, and that is because as you are kind of moving through those elements, a new electron is being added to an S subshell. The block on the right is known as the P block, because as you move through those elements, as they gain electrons, they're adding new electrons to a P subshell. The section in the middle here is commonly known as the D block. Sorry to be kind of cramming that in, because you're adding electrons to a D subshell. And then the little island of misfit elements down here is known as the F block, because you are adding electrons to an F subshell. So the positions on the periodic table, in terms of what block it's in, correspond to what type of subshell you're filling. The rows correspond more or less to what shell you are in. So the first row of the S block is where you are putting electrons into the 1s subshell. So the reason why I left helium out over here is because helium and hydrogen both are a little bit strange in their behavior, because they are so unique in that they only have 1 or 2 electrons, that their electrons are all in a single subshell, a single orbital, makes their behavior a little bit different. So for the purposes of electron configuration, you should really think about helium as being over here. For the purposes of electron configuration, it is part of the S block because there is no P subshell in the n equals 1 shell. So the first, bump this up another notch, the first couple electrons, that is too fat, never mind, down 1, here we go. The first couple of electrons, first 2 electrons go into the 1s subshell, and as you go down the column, each row is the next S subshell. So moving through this section, you'd be adding electrons to the 2s, 3s, 4s, 5s, 6s, 7s. Over in the P block, as you move across, you're adding to one of the P subshells. The first row of the P block is the lowest energy P subshell that exists, which is the 2P. So moving through here, you're adding electrons to the 2P, and then every time you move down a row, you're moving up a shell. The D block is where people tend to get a little bit confused. But if you apply that same principle of thinking about the first row of the D block is the first time I'm ever going to encounter a D subshell. If we think about what we talked about yesterday, the lowest energy shell where a D subshell is found is the n equals 3. So the first row of the D block represents the 3D subshell, which is a little weird because if we're thinking in order, we have 4S and then 3D and then 4P. But if you go back and look at your orbital diagram from the previous video, you'll find that that matches, that was where we started to get that weird crossover between shells, was at this point. So the first row here is the 3D, and then we go to the 4D, the 5D, and the 6D. And we're filling that as we move across. And then in the F block, the lowest energy shell where you find an F subshell is the n equals 4. So these rows represent the 4F, and 5F subshells respectively. So then the only other thing you need to keep in mind is, where does this block actually go? It's usually depicted sort of off by itself, purely because that makes it fit better on a piece of paper. That is literally the only reason why it is pulled out by itself. But these little stars are showing you where this matches up. So this section of the periodic table actually belongs in between the S and D blocks. It just only applies down in these rows, since it's much later in the numbers that you find it. So if you follow the atomic numbers in order, you can figure out where to fit it. You'll note that there's a big gap here. We go from 56 to 71. 57 through 70 is the top row of the F block. So using this, we can figure out our electron configurations just from looking at the periodic table by just following these sections in order. So I'm going to do an example so you can see what I mean by that. Back to a reasonable writing size. There we go. So let's write the electron configuration for arsenic. So arsenic is element number 33, is over here on our periodic table. So you will notice that it is in the 4p section of the periodic table, which means that the last electrons I place, the highest energy electrons I place, are going to be in the 4p section, but I'm going to fill up everything else before that first. So I usually just start at element number 1 and work my way through the numbers until I hit my target. So if I start at element number 1, that's the 1s subshell, and I can put 2 electrons in there, so that takes care of electrons number 1 and 2. Electron number 3 is then going to go in the 2s, as well as electron number 4, so that'll be 2s2. Then we jump over to the p side of things for electrons 5 through 10. So that'll be 2p6. Electrons 11 and 12 go in the 3s. Electrons 13 through 18 go in the 3p. Oops, I screwed up. This was supposed to be an s. 3s2, 3p6. There we go. So that got us through 18. 19 and 20 go in the 4s. 21 through 30 go in the 3d. And then 31, 32, 33 go in the 4p. So that's 3 electrons end up in the 4p. Everything else before that is full. So we're just following the numbers in order through the periodic table and recognizing the appropriate subshells that go with sort of each section until we get to our end goal. So as you can see, electron configurations start to get kind of long. That this is the electron configuration for arsenic. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3, and that's only element 33. So imagine if you wanted to write the electron configuration for something like barium or uranium or something down near the bottom of the periodic table. It's going to get really, really long because we've got lots of subshells to list. But we do have a way to abbreviate it. So we use what's known as the noble gas abbreviate. The farthest right column of the periodic table is known as the noble gases. I swear. So that is this column here: helium, neon, argon, krypton, xenon, etc. Those are known as the noble gases. They are very stable because they have filled electron shells. We'll be talking more about this as we go through the next couple lessons and units. But the standard way to abbreviate a longer electron configuration, or really you can do it with any electron configuration you want, is by referencing the previous noble gas and then listing anything additional. So, for instance, if we wanted to abbreviate arsenic, what we would do is look at where arsenic is on the periodic table, work backwards in numbers until I find myself at a noble gas. So you're always essentially moving up a row to the farthest thing on the right, and I find that the previous noble gas is argon. Argon is at the end of the 3p, which means that everything from the 1s up to the 3p would be my electron configuration for argon. So my abbreviated electron configuration is to say everything is the same as argon, and we put it in square brackets, the symbol for the noble gas, and then we just list anything else that comes after that. So arsenic is the same as argon plus these extra pieces, plus these extra bits. So I would have argon 4s2, 3d10, 4p3 would be the abbreviated version of this electron configuration, which is a lot shorter, which is nice. If I don't specify, you are always welcome to use the abbreviated configuration unless I ask you for the complete configuration, which I rarely do. So feel free to abbreviate or not, as you prefer. But it can come in handy, especially for the later ones. So again, we're just taking the previous noble gas and adding on the extra pieces. We can see that this would be the configuration for argon if we worked that out. So all of this is encompassed in these square brackets here, and then we're just adding the additional stuff at the end to say it's argon plus a few extra things.